a researcher and developer of computer-aided music composition software at IRCAM in Paris. And this is John McCallum. He's from UC Berkeley, and he works as a researcher and a music application developer, and he's also a composer at the Center of New Music and Audio Technologies, the CENMAT. So we're working on different projects that we are going to present right now that differently relate to functional programming and that we have tried to put together in this work. So the main idea of this paper is to show or to study if inter-application networking can be improved by a structured communication through technologies that are developed at CENMAT, the OSC format, and the Odot library that John is going to present right now. So I will let him speak first, and then I will show you some of the use cases and applications we've been studying in this work.
Thank you. Okay, so I'm going to talk about ODOT, which is a project that's been going on at CENMAT for a while, but I'm going to start by talking about Open Sound Control, which sort of is the data format that underlies this thing called ODOT. So Open Sound Control, or OSC, it's a sort of lingua franca for interactive media arts programming. It's a binary encoding. You'll often hear it referred to as a protocol, which it's not. It doesn't say anything about transport or anything like that. It's essentially a key value store. There are lots of these in the world, and this is one of them. We like to think of it as punctuation in the sense that it can be used to clarify the meaning of the data that it encodes, and you can read all about it at the specification here. So an Open Sound Control message looks something like this. It's composed of an address that binds some data. It has some type tags that refer to the data and allow you to interpret what those things are. Everything is null padded and 4-byte aligned, and there's a little length. The length of the message is at the front of the message. So these things can be sent separately, or they can be packaged together in what we call a bundle, which is just a key value store, a dictionary, or whatever. A bundle has has an identifier at the beginning, and also a 64-bit fixed width NTP style time tag. So it also supports pattern matching. So if I have these addresses and I'm trying to address some synthesizer or whatever, I might have a couple of different voices of a synthesizer. I can refer to all of them by substituting this one for a star. I can do a range of them. I can do a little subset or whatever. So that's more or less everything you need to know about Open Sound Control, as fast as I can possibly say it. There's a little bit more in the specification, but not a whole lot. So this project, ODOT, is a superset of OSC 1.1. It simply adds a couple of extra types. The open in Open Sound Control doesn't refer to open source necessarily, but it refers to the openness of the specification in the sense that you can add extra types and extend it and so on. It's a dynamic programming environment. It's embedded in a host environment. It includes a small, lightweight expression language evaluator, and you can find it on GitHub. And so what it allows us to do is take an Open Sound Control bundle, which is a time-tagged, ordered list of messages, do some atomic processing on it, and produce a modified copy of this thing. So it exists in implementation in a variety of different environments, including Max and PD, which are sort of important media arts authoring environments, as well as open music, which Jean is a developer of, and we'll talk about extensively in a few minutes, as well as Python, JavaScript, Node.js, and so on. I'm going to skip over this for now. And I'm going to give a short example in Max MSP. If you haven't seen Max before, all you need to know about it at this point is it's a visual kind of data flow-like programming language. Data flows from top to bottom. By convention, objects that have multiple outlets fire from right to left. And also by convention, the leftmost inlet of an object is typically the one that triggers some operation or some computation and possibly some output. So here we have a data source, in this case UDP. We're visualizing the data. It's the same as the example we just had. So I've got a gain and a frequency parameter for two different synthesizers, notated as synth 1 and synth 2. And I'm going to transform it by just simply reinterpreting that frequency in hertz as a MIDI note number and converting the gain in dB and decibels to linear amplitude. So the way we go about this is to first make a copy. unbind the pieces of data that we're interested in. So we're taking it out of the ODot framework, and now we're going to interact with the host environment. Here we're going to use two built-in functions from Max, F to M, which converts frequency to MIDI, and decibels to amplitude, dB to A, which converts decibels to linear amplitude. We then rebind these things to new addresses, so we're entering back into the ODot environment, and then we merge the result of that with the original, with a copy of the original. This is great and everything, except that we have a whole bunch of problems. One is that all of this stuff is not atomic anymore. We've lost our documentation, and by which I'm referring to the addresses that gives some interpretation of what that data is. We lost the timestamp, and we may have incurred some sort of implicit type conversion when we crossed out of ODot into Max. That's a scary one because I can't look at this picture and tell you if we did that or not, because different versions of Max support different types. So we can fix that by replacing all of that stuff with a call into this expression language. So here what I've done is just written a simple expression that calls a built-in function F to M, which converts frequency to MIDI. There isn't a built-in decibel to linear amplitude function, so I've written a short expression, and these are just done with assignment, and then you produce this copy. We can go a step further and actually take and hoist out these expressions into the data that they actually refer to, and that's done like this. So here I've created a function called slash dB to A, which is just a lambda around that expression. And then I have an expression called slash expr that actually does this conversion in the assignment. So here what I've done is I've tried to decouple the what of computation from the where of computation. So those things are separate now. So the idea that we're going to talk about with Jean in just a second is that here we're operating in a single environment, but this expression evaluator can live in different environments and provides a node for computation in a variety of places. So this is the thing that allows us to communicate across these different environments. So we have a shared data structure, we have a shared small language, and each of these places becomes a site for evaluation of that without having to necessarily exit into the host environment. So just before I turn it over to Jean, I'm going to mention a couple of words about the expression language. Like I said, it's a small, lightweight functional expression language. It has function abstraction, higher order functions, no side effects. Those are the good things about it. The less good things about it are that it wasn't really designed. It was meant to be a very, very small expression language, just with maybe a dozen operators at most. And it's sort of designed through feature creep. So that's resulted in a fairly brittle and awkward syntax, although it's quite usable and is being used by a fairly large community in Berkeley. It also sort of annoyingly has a couple of languages embedded in itself, which I can't really explain. The good news is that we're hard at work on version 2, which is, let's just say it's designed as opposed to well-designed. It's got more robust syntax and semantics, and it makes no distinction between data and code that operates on that data. So with that, I'll turn it over to Jean.
Okay, so the second part of this work concerns the open music computer-aided composition environment. So just a few words about it. So it's a visual programming language that is completely built with and on top of Lisp, which is used by composers to do a whole variety of things related to their compositional activity, like generating scores, sounds, transforming any kind of data or structure. It's just to allow composers to program. It is based on demand-driven execution, which means you have some visual programs, as you see on the left, which, as the contrary of Max, are kind of static representation of a program that you evaluate at some point to update the value of some nodes of the graphs. It also has some kind of local state by the use of some specific box that you can see also on the pictures, which store the temporary state of some data, which you can interact with by specific editors and visualize, edit the data, scores, sounds, any kind of data structures. And it has a whole set of libraries that allow to make some specific use of it for either specific computing paradigms like constraints or the other things, and also address some specific musical applications like sound processing or spectral music, algorithmic music, and so on. If you're interested in more of how is it actually useful, I would recommend to read or to have a look at these books. It's 3 volumes called the OM Composers books, and the last one is about to be published within a few weeks, I hope. So it gathers about 60 chapters of different composers which explain how they use this language or this environment for their everyday work as a composer. And it turns out that currently and more this environment interacts with other frameworks and other applications, especially real-time environments like Max or other similar systems. Some recent applications of this have been, for instance, some works by composers using external device to interact with the Open Music Visual Programming Framework. Control of real-time audio processing or spatialization that's done typically in real-time audio environment, and we're interested to do all the authoring part in Open Music, typically generating a lot of control data and all the DSP real-time rendering in audio environment. I'm going to show a little demo about this right after. There's been also works on at the bottom left, it's an Open Music Visual Program that interacts with an orchestration server to send requests, get some results from search of instrumental combinations, or human-computer improvisation, where typically a performer plays and interacts with the compositional environments, which generates some kind of accompaniment, which is generated from the player's music, and which also will influence his playing. So in all these kind of applications, we believe the ODOT library that John just presented will allow us to talk to each other, not only by sending data, but also using functional specifications and programs, and we hope this is likely to improve the communication. So, as mentioned also, Open Music is now one of the host environments for ODOT. So, being a host environment is not very difficult. It's just a matter of linking the library or binding the library if we are, as in this case, in the Lisp environment. And then you can build some tools on top of it. So, in Open Music, we have 3 main domains of applications of ODOT. First is to create OSC bundles from messages, so we can format OSC messages, make these bundles. We can receive these bundles from network or send them back through UDP, typically to other framework environments. We have a set of tools to format the ODOT expression in this syntax that John mentioned, which is maybe not definitive. This is the version 1.0 of the ODOT expression language. So you can either write them textually or generate them by evaluating the kind of graph of functions that's at the top of this picture. And the more important is we also have the interpreter that's embedded with the library and allows us to evaluate this expression on the data that we generated or that we received from somewhere. So from this, I'm going to switch to a quick demo. Your screen. Okay, here we go. So here I am in the Open Music environment, and this is a simple program that will generate some spatial data. So that's an application, as I mentioned before, of imagine I want to generate some trajectories for spatializing sound using a multi-speaker environment. So I have a program that I've pre-designed. I'm evaluating it, and I'm getting this 3D structure here. So when I have this kind of object, I can play them. So if I play a trajectory. Basically, it does not much by default, but I can choose to assign actions to it. For instance, well, this is a basic print, or I can send the values as OSC to another environment. So I'm going to first, okay. So now I'm in Max here. So also it's important to mention that usually Open Music users and Max users are different kinds of users. And for instance, if I'm comfortable to programming in Open Music, I would not necessarily be in Max. So for instance, here I have a Max patch, and I will say I don't want to program this patch much more, and I will do try to move most of the programming in Open Music and the execution in Max. That's the kind of the purpose of this demo. So if I just play this here, I will send this information to this Max environment. I don't do any real-time audio here, but you can imagine this controls some audio, and this is just the display. Now, if I want to send not one, but say 10 or 50 sound sources, I have different options. I can either program this patch much more complex in Open Music to send a lot of data, but most probably what happens is I'm going to overload the communication. So the solution here is to program some functions with these Odot tools and generate a bundle. Here, well, you cannot see very well, but inside is some expressions that I wrote in the Odot expression language, which basically, given a number of sources, here is 5, will distribute them around the given position. I just assign this action to my curve here, and now what's going to be sent through the network is this 2-dimension position plus these functions that say, if you want to spread this to n sources, you can just do it like this, and that would generate more sources. So the result is here. Oops. I'm gonna put it in a. So now this is what I receive in Open Music in Max. So you see here, I receive just a little bit of data and some functions, and this is how I decode it by my. At the right is how I decode it by evaluating the functions that I've written in Open Music, and I also have a switch here which allow me to switch between different evaluation functions that I've been proposing in my Open Music patch and distribute the sources differently. And you can of course imagine that I can program some new functions here or change for a different interpretation of this data. Did I forget something? No. Just very quick. So. I'm not getting too much into details, but in the paper we also show another example of an application. It's about receiving data from a real-time video stream. It's an experiment we've done with another composer from UC Berkeley, Rama Gottfried. So he has some data coming from real-time capture and motion contour recognition. It arrives as raw data in Open Music. And if we program some mapping between the raw data and some graphical settings in Open Music, we can have some more easy visualization, which allows him to do some just visualize or edit a little bit the data stream. And he could also program his own mapping functions using the Odot expression language, sending these mapping functions to Open Music so that the display is different than what would have been the default display in the environment. So just to wrap this up a little bit, so what we have trying to experiment with and show in this paper was that embedding functional specification and programming within the OSC structures that are being transmitted quite extensively between music and media environments could be useful to optimize and extend expressivity in this inter-application communication framework. It's interesting that the data, this function operate directly on the transferred data. There is no much encoding, decoding to perform. What else? And yes, and the sharing of this common environment is also a convenient feature in terms of being able to program in the same language, whatever you're a Max user, you're Open Music user, you're in Python, you're wherever, and freely decide where the programming and the execution takes place between these all set of possibly interacting applications. And that's it. Thank you.
So, except for the programmability, what's the relationship between the ODOT stuff and MIDI on a total layperson?
So Open Sound take the mic. Open Sound Control in some ways was in response to MIDI. So there are a number of things. I wasn't around when it was designed, but you know, MIDI's model of music is based on the keyboard, and you know, that you run into problems all the time if you want to deal with microtones or whatever. So the idea was, let's have a more open specification for how to address a synthesizer, essentially. So in some ways, it's a response to it.
Since MIDI has been used in so many domains, even other than music.
Same with Open Sound Control. It's been used for show control and all kinds of stuff. Yeah.
You mentioned the fact that there are several places where you can choose to implement a certain logic. And how do you decide? So you get things like, oh, this thing you would do in Max because it's more about the end. But yeah, how do you decide which tool you will use for certain logic what you produce?
Well, there are several answers to that. There are some, the different tools are typically designed for some specific application. If we take Open Music and Max, so Open Music typically is for building structures which have kind of a temporal extension, and you want like typically a score, a whole sound. In Max, you would develop more processes that relate to interaction, like I want to respond like this to some things that happen. So there is this, but there is also the fact that you can also tweak the environments to do whatever you want. So it's also a lot of personal preferences of the users. Like some people, they use Max and they just want to use this environment and they try to do their best to do, you know?
But Odot is right in the middle, so you have to have more choices.
Yes, the idea is this library is just a library that anybody can link, much like if you use I don't know, lib sound file to play or read or play sound files, and you would use this library to, if you want to deal with OSC programming and encoding. So if everybody, or if at least the two or more applications link to the same library, they can talk to each other.
Yeah, the lib sound file example is a good one, because what you can say is, well, you know, some low-level C API for dealing with audio. If you work with it in C, you just call the functions directly. But if you want to wrap it in Python, there are like idiomatic ways of doing it, and you might have a couple of different different developers that do it in different ways. So we don't over-specify. In fact, we don't specify that at all. But it should. We hope that each implementation would be sort of idiomatic for whatever host it's in. Good.